In this final example, we have a cart sitting at the top of a hill, a perfect circular hill. Somehow, right at the edge, this cart gets just enough initiative to start heading down the hill, but starting at 0 velocity right here. And the question is, where does the cart leave the hill? And what we talked about in class last time is, certainly while the cart is up here on the hill, there's a substantial normal force that the ground is pushing up on the cart to keep the cart from falling into the ground. But as we go around the curve, that normal force diminishes for two reasons. One is that the direction of the positive gravity force is moving further and further away from the slope angle, and so we're not getting as large a gravity effect pushing the cart down. And the other is we have an acceleration because we're traveling on a curve. The cart would prefer to at any point leave and travel in a straight line, and that tendency gets greater as it's moving faster. And so we are then told that a small vehicle enters the top A of the circular path with a horizontal velocity v0. Okay, and that didn't say 0. And it gathers speed as it moves down the path. Determine an expression for the angle beta to the position where the vehicle leaves the path and becomes a projectile. Evaluate your expression for v0 equals 0. Neglect friction and treat the vehicle as a particle. This final piece, treated as a particle, means if it has any energy that comes from the rotation as it rotates around the hill, we're going to be ignoring that effect. And so we will again draw a free body diagram of the cart somewhere in the middle of its travel, and the only two forces acting on the cart, and that would be a normal force acting, pushing it up, keeping it falling down into the ground. Now notice that our normal unit vector, though, is here. Normal force is normal unit vector pointing inward, normal force pointing outward, so normal force in our normal equation will be a negative quantity. And then we have a gravity in the vertical direction, and we'll have a component of gravity in the normal direction, and we'll have a component of gravity in the tangent direction. The tangent piece will be positive, and the normal piece of gravity pointing in toward the center of the circle will also be positive. Now, this problem basically is the same as the girl on the swing problem that we looked up earlier, except it's been inverted. And we are going to increase velocity as we travel through the problem. Velocity is not constant, and so we're not going to have a constant acceleration for this problem, so we can't use constant acceleration problem equations. We will have to integrate. And so if we this time first sum forces in the tangent direction and set it equal to mass times acceleration in the tangent, which is not a constant, then, and here is our tangent direction shown, and so the forces would be in the tangent direction would only be a piece of gravity. There is no component in the tangent direction from the normal force. Okay, and so the component of gravity is the sine component. So mg sine of theta is equal to mass times acceleration in the tangent direction. We can cancel the mass from both sides of the equation, and we get that the acceleration in the tangent is equal to g sine of theta. This is starting to feel fairly familiar, and now we're going to set up an AdV equal VdV integral. V on the left-hand side, the acceleration tangent will be written as g sine of theta. Now, let's take a look at our dr thing. As the cart travels in the tangent direction, causing theta to get bigger, does s get bigger, the distance traveled, get bigger as theta gets bigger? In this case, yes, they both become more and more positive. Therefore, this time, we're going to say that ds is equal to positive r d theta, where last time we said it was equal to negative r d theta. And again, that's because theta gets large as s gets larger. they both become more positive. Doing our integral on the left-hand side, we're going to get a v squared over 2 difference because of the two limits of integration. And doing this integration on the right-hand side, where we've substituted in, I better zoom out a little bit now. That's too much. Okay, a has been replaced with g sine of theta multiplied by rd theta. Integrating this one, we get a 2g r1 minus cosine of theta. We start to notice that on swing programs, we get our spring problems, we get this r times 1 minus cosine of theta almost every time. And so now we've got a relationship between our final velocity at any angle theta that we care about and our starting velocity and the geometry of the curve and gravity. Now that we have a means of finding velocity at the point of interest, we will now sum forces in the normal direction at that point of interest. And looking at the free body diagram, normal forces will include a positive piece of gravity and a negative normal force. So positive mg theta minus the normal force is equal to mv squared over rho. And we have a means of knowing v squared, so we can substitute that in, and then let's work out our algebra that for any given starting velocity v0 that shows up in this equation, we'd be able to determine for any angle our final velocity. But this thing says, let's see, in the normal direction, this equal to mv squared over rho, and we're going to pay attention to our normal force going to 0. That's our key idea here. At impending leaving of the curve, when we're fixing to leave the curve, that normal force goes to 0. So let's solve this equation for the normal force actually in terms of everything else, and then we'll be setting it equal to 0. So normal force equals, and this v squared term has been substituted in from above. The normal force equals a gravity term plus other terms. Let me move where you can copy that one. Then finally, simplifying a little bit, the normal force is equal to mg times all of this. And this involves a v0, and it involves the cosine of theta. Now our question is, since normal force goes to 0 at impending slip, we'll set this equal to 0. We'll plug in whatever value of v0, the starting velocity we choose. In this case, that's going to be 0. And then we can solve for the only unknown, the angle theta, at which we leave the hill. So doing that, normal force goes to 0. The particular theta when we leave the hill, let's give it a special name, beta. And so we can solve our earlier equation for the value of beta based on a value of v0, and beta comes out to be the inverse cosine of 2/3 plus a v0 squared over 3g big R. We were told in this example to go to a velocity of 0, and with a starting velocity of 0, we come up with a beta of 48.2 degrees. Okay, if we were going a little bit faster, if we had a 1 meter per second velocity, that extra speed at the top will cause us to fly off the path earlier because we're traveling faster all the way along, and that particular value would be a 42.7, which is smaller than the 48.2 that we saw for starting with zero velocity. Of course, the dilemma is if we start with 0 velocity at the top of the hill and we're at the very top, then why do we ever move? And the answer is we assume that we started with incrementally close to 0 velocity and therefore did begin to move. And that's the end of this problem.